Hey, so welcome back, and this is another daily code problem. So today it's called House Robber, and it's a medium level dynamic programming problem where essentially you're given an array nums, which basically just represents for every index, it's the house number. And so at index 0, it's really house 1, so it's kind of one index based. And the value stored here represents the amount of money that you would make by robbing that particular house. And so essentially all that you want to do is you want to maximize the amount of money that you can rob. And the only constraint that you have is that you can't rob adjacent houses or really cells that are next to each other. And so you can't rob 1 and 2 in this case, but it's fine to rob 1 and 3. Okay, so what the decision tree looks like here is something like this. So you could either rob the first house for a value of 1, or you could rob the second house for a value of 2. If you rob the first house, then you could either rob, say, the next house for a value of 3, or the last house here for a value of 1. But if you decide to choose to rob house 2 initially, the only thing left you can choose is to rob house 1. And so naturally, for this question, we want to get the maximization of the amount of money we can rob. So that would be this path here, which would have a total sum of 4. Okay, so to do this, I'll first show you the top-down memoization approach, and then we'll do the bottom-up one. And so typically, when you do the top-down approach, it's very easy to translate what we just saw there with the decision tree into kind of a recursive relationship. And so we're going to define our DP function, and generally you cache this. It's just kind of a typical pattern. And we're going to specify an index, and we're going to start at 0, and we're going to kind of build up to the end of the list, starting from left to right, essentially. And so the first thing is we'll need to specify our base case, and that's going to be, okay, if I is greater than or equal to the length of the numbers, then naturally we're going out of bounds, and we're just going to return 0. And that's because you don't get any extra money by going out of bounds or kind of reaching the end of the houses. So we're just going to return 0 in that case. Otherwise, we're going to return our kind of recursive relationship that we just were building. And what that's going to be is the maximum of those two choices that we can make. And that's going to be, okay, either we can grab the current number and recursively call I plus 2. And so we can't grab the one next to us, but we can go to the house like next door. Or the decision we can make is, okay, otherwise, let's go ahead and just grab the money from the house next to us and just not even consider the current house. And success. So now if we want to convert this into a top or bottom up solution, which typically you can actually get some space optimizations here, and we're actually going to do that now. And that's because with this, like, you're storing basically O of n, because you want to consider, like, at each stage in this step, you're kind of calculating, or you're storing the value that you just made. So it's kind of O of n space complexity. But with this bottom-up approach, you can actually do some space optimizations here, so that you only have to have 2 pointers, which kind of point to the last 2 houses that you just considered, and then another pointer just keeping track of the running sum or the maximum sum that you're propagating forward. And so what that looks like is initially we'll just have like house 1 and house 2, and they're just going to be set to 0, and that's because it's just pointers that just represent, okay, what's the sum that you would have for those 2 previous houses. And so we're just going to kind of move once again from left to right. So we're just going to iterate through the numbers in this array. And at the end of this, we're going to return house 2, because that's always going to be the larger number. And we're going to say, okay, let's calculate the maximum. So what that's going to be is, okay, the current maximum is just going to be either the current amount here. So this number, we can call this amount. And we can add here the house 2. or really house 1 because that's the house that's furthest away, or we can grab the house that's literally just next door to us. So it's kind of our next door neighbor behind us. And then after this, you just need to make the swaps. And so, okay, now our house, let's see here, house 1 here is going to be equal to our house 2. And then our house 2 is going to be equal to this new maximum. And that's once again representing that, okay, the largest number is always going to be pointing to house 2 here. Let's go ahead and run that. Oh, and we don't need this. Now let's go ahead and run that. Looks good. And success. So yeah, that's today's LeetCode problem. So I hope it helped, and good luck with the rest of your algorithms. Thanks for watching.